deviation of the sample means, the mean and the standard deviation of the uh, X bar values. And we know that different samples, folks, this is going to be a recurring theme for me. Different samples will have different means, and the sampling distribution is the probability distribution of these different sample means. And when we calculate the mean and the standard deviation, we designated them specifically. The mean of the sampling distribution is mu x bar. Mu x bar. The x bar reminds us that this is about the sampling distribution of the sample means, and mu is obviously the mean. So mu x bar is the mean of the sampling distribution, and sigma x bar is the standard deviation of the sampling distribution when we are working with sample means. All right, this is new to us. So one more time, folks, we are talking about the mean and the standard deviation, sigma x bar. All right, so the mu x bar and the sigma x bar will help us remember that they are different from mu and sigma. We have some rules. Okay, the standard deviation of the sampling distribution, sigma x bar, is sigma divided by square root of n. N, little n, I should be careful to say little n. Little n is the sample size. Okay, and we use this formula if you see the point that's highlighted in red. When the sample size over the population size, the ratio is less than equal to 0.05. This is very, very important. And when this ratio is not satisfied, when sample size over population size, this condition, again in the red, is not satisfied, we calculate the sigma x bar a little bit differently. We apply what's called a finite population correction factor. Excuse me. All right, folks, this is a point, especially this point is often confusing to students. These two equations apply when we know both the sample size and the population size, and no other information is available about the population or sample. Confuses students a little bit later. Be always smaller than sigma or sigma x. Sigma x is often something we don't remember to say, because sigma x is basically the population distribution. Okay, so another way to remember point 1 is sigma x bar is sigma. It's simple mathematics, simple arithmetic. Anytime n is greater than 2, greater than or equal to 2, sigma x bar is going to be smaller than sigma. And now, in terms of the bullet point 2, we actually have some evidence. Okay, so if you would please, folks, go ahead and read the example, the statement in example 7-2. Which equation do I need to use? Do I need to use this equation? Or do I need to use this equation? All right, so I'm going to pick on 3 of you. And finally, Shakin is Zaman, right? I can stick to this equation. I don't have to worry about the correction factor. All right, so you see in part A, the small n over capital N is 0.006. which is smaller than 0.5. So sigma x bar is sigma divided by square root of n. 3.7 divided by square root of mu x bar is same as mu. That doesn't change. To the sigma x bar went up. Also calculated thing, but I'll tell you anyway. So it's minus 3. That means, okay. So now we are going into the same shape of the sampling distribution of x bar. All right. We are going to look at two scenarios. The first scenario is the population has a normal distribution, and the second scenario is the population does not have a normal distribution. So now we are getting a little bit focused that now we have some additional information about our population. Okay, folks, one more time, and this is where students start to get confusing in my experience. It's a little different. We symmetric bell-shaped distribution with one peak. And the beauty of the normal distribution is something that we learned in chapter 6. We can standardize a normal distribution and use the Z-table. We will do the same here. So normal distribution is important to us. And the rule is if the population is normal distributed, then any sample that we take, regardless of the size, any sample that we take, the sample itself will have a normal distribution. That is important because, again, if the sample has a normal distribution, that would allow us to use the normal distribution, standard normal distribution table. If I know my population has a normal distribution, then any sample I take from it, regardless of size, will have a normal distribution. So my first sample is a sample of 5, has a normal distribution. My next sample has a sample of 16, normal distribution. My next sample has a sample size of 30, normal distribution. Sigma x bar is sigma divided by square root of n. And as we are increasing samples data, go ahead and look at this, or rather review the problem statement. All examinee, that means population, is normal. The population has a normal distribution. This is important. Couple of things here. One, I do know that my population is normally distributed. So that tells me that any sample that I take from it will also have a normal distribution. And second, nothing here gives, to avoid the confusion, mu is 1020 and sigma is 153. Great. So divided by square root of n. So in all three cases, mu x bar is 1020. In A, B, and C, mu x bar is 1020. Mu x bar is mu 1020, sigma x bar is 153 divided by square root of 16. Sigma x bar is 38.25. Any question, folks? And a standard deviation of 153, and that narrow 3 over square root of 1000, 4.838. And now, folks, you should have seen. All right, now another extremely important theorem for us is this theorem of central limit, is the theorem named central limit theorem. This is a very, very practical practical application for us. Okay. Population distribution, or we just don't know, or we know the population does not have a normal distribution. Take a sample size that's large enough. That's it. That's the central limit theorem. If the sample size is large enough, we can say our sample is approximately normally distributed. And if our sample is approximately normally distributed, we can take advantage of the central limit theorem. And if my sample is approximately normally distributed, folks, guess what? I don't have to worry about these two issues. Make sure our sample is large enough and distribution. Approximate. My sample is skewed to the right, but what we okay, very is 1550, same as mu 100. We were told that it is skewed to the right, so we have a skewed to the right distribution, whereas when my sample size is 30, central limit theorem lets me say my sample is approximately normally distributed. So here you have a bell-shaped distribution, symmetric distribution, with a mu x bar of 5 per root of n. 100, my sample is approximately normally distributed, is different to 6% within plus minus 2 standard deviations. Z equals to plus minus 2. After 7, we are looking at the probability distribution of x bar 68 and standardizing it to a standard normal distribution, so we could use the Z table. We can do the same with the x bar values as well. Highlighted. I can say my population is normally distributed. That's important because if my population is normally distributed, all samples from that population will also be normally distributed. Okay, my population mean is 32 and my population standard deviation is 0.3. My sample size is 20. Okay, so mu x bar is same as mu 32. Sigma x bar for us is 0.3 divided by 20, 0.0670804. Any question to this point, folks? Same standardization equation, but modified because we are working now with the sampling distribution of the sample means. Score, look up the two areas, and the difference between the two areas is the probability. So it's a simple standardization X problem now. When X bar is 31.8, my Z value is negative 2.98. When X bar is 31.9, my Z value is negative 1.49. We look up the area to the left of negative 1.49. That is this value, 0.0681. When we look up the area to the left of negative 2.98, we will find this value in the table. And the difference is the probability that Z is between negative 1.49 and negative 2.98, which is also the probability that my X bar is less than 31.9, but greater than 31.8. And here's the visualization, folks. We have a my population 0.49. Okay, Avijit Sarkar, unmute your microphone. Do we have any clue, anything, this example statement that says my population is normally distributed? So we don't know. But there is some good news. My sample size is 400. Why is that important? That distributed. Okay, the second one is lower than the population mean by 50 or more. Go ahead and do that. My population mean is 3173. My population standard deviation is 750, as Avijit said correctly. And All of you need to be confident. If you are paying attention, that should give you confidence. Normal. So my sigma x bar is 3750. And now looking at part A, remember in part A, folks, if I may, within 70 of the population mean. Population mean was what? 3173, right? I forget. Yeah, 3173. So within 70 of the mean, within. So part A, we are interested in 3103. How did I get here? Well, mu minus 70. Also interested in 3243. How did he get here? Mu plus 70. Okay, so we standardize those two x bar values, get z values of negative 1.87, positive 1.87, and we look up the areas on the from the table. Fine. Problem statement ultimately is a simple standardization problem. 7. Do part negative 1.33 lower by 50 or more. That means lower by 3123 or even smaller than 3123. We are looking for the probability that the average credit card debt is 0.91. So here is the final conclusion to part B. Folks, any question about this example? and how that relates to population proportions. So far, we have dealt with sample means and how these x bar over capital N is population of the sample. And as what we saw in with sample means, same thing will play here. You'll see here. Different samples may have different proportions. All right, so let's push on a little bit more. We have this many in a city, and this many that of the total in the city that owns their own home. And then we do a sample of 240, and out of that sample, this many own their own homes. So the characteristic that we are looking for is people who own their homes. All right, so let's calculate the population proportion. Proportion P hat is 158 over 240. Here, folks, you have the calculation. The population chapter 6 in the next class. We'll